was. All right. Our next speaker, Schramm from Stanford.
Hey, everyone. Thanks for inviting me to participate in this workshop. So I'll be talking today about the higher dimensional expansion of random geometric graphs / simplicial complexes, but we're going to focus on kind of a graph picture because I think it's easier to introduce the definitions in that way. And this is based on joint work with Siki Liu, Siddhant Mohanty, and Elizabeth Yang. And I see at least Siddhant and Siki sitting in the audience here. So I've got a backup in case we need to call it in. Yeah, this is not exactly a learning theory topic nor optimization topic yet, but perhaps.
Please don't draw attention to that.
Excuse me. But I'll try to make a case for why it kind of is related a little bit later, just for Adam, so that he's not so embarrassed. Okay, so let's just get started. So we say that a graph is a lambda spectral expander. If the second eigenvalue of G's normalized adjacency matrix, which I'm just going to denote like this, is upper bounded by lambda, which should be strictly less than 1. And expanders are one of the best things that happen to theoretical computer science, I think, ever, because once you have an expander that satisfies this property, you get all kinds of consequences, which are really, really nice. Like, for example, a graph which is an expander has no sparse cuts. So that's some kind of measure of the connectivity of the graph. And also you get some other nice consequences like random walks mix fast, etc. And this makes them really useful in all kinds of applications, like like in error correcting codes or designing failure tolerant networks and stuff like this. Okay, so expanders are great. And the first time that you hear about an expander, you have this graph and it's really well connected. So maybe it's at first surprising that you can get expanders which have constant sparsity. So there exist expanders with the number of vertices n going to infinity, but average degree or maximum degree constant. Like. And it's not even that this type of thing is rare, because it turns out to be the case that if you sample a random graph, then a random sparse graph, then it will with high probability be a expander. So here's a theorem. The different parts of it are due to Alon and Friedman. It basically says the following. A random irregular graph meaning like a uniformly randomly sampled irregular graph has the best expansion possible among all the irregular graphs. Okay, and so what this means is that the second eigenvalue is going to be like this number, which is called the Ramanujan bound with high probability. So we learned that expanders are not only awesome, but they're also abundant, right? And because random graphs have this expansion property, so for me at least, it gives me a way to think about what an expander is, because I can just think of this nice distribution, which I'm pretty good friends with. Okay, but so now maybe you're happy with this situation, but there's now a higher dimensional notion of expanders, which I will introduce in a second. Kind of this comes from the thinking. Okay, so we know what expansion means for graphs. We're satisfied with it, but we want to now think about what it means for hypergraphs or simplicial complexes. Okay, but in order to make the definitions more accessible, I'm only going to be talking about graphs. So for today, if you're kind of like a hypergraph / simplicial complex expert, this might look a little funny to you, but I'm just doing this so that we can do the definitions efficiently. Okay, so in order to introduce what a higher dimensional expander is, I'm going to introduce the following concept. So if I have a vertex in a graph, I say that the link of the vertex is just the graph induced on the neighborhood of that vertex. So let's just do an example. Okay, so in this graph, what is the link of the vertex A? Well, it's supposed to be the induced graph on the neighbors of A. So what I would do is I delete A and I delete all of the vertices that aren't touching A. And then the link of A just ends up being the 4 cycle of the neighbors around it. Okay, this is the link of A. Let's do just one more example. Let's call this vertex B. Okay, when I delete B and all of the rest of the vertices that don't touch B in the graph, I just get an independent set on 3 vertices. So link of B. Like that. All right, now I'll say that a graph G is a 2-dimensional expander. Okay, a 2-dimensional spectral lambda expander. If the following conditions are met. So first, I'm going to require that G is connected. Fair enough. Then I'm going to also require that for every single one of the vertices participating in G, the link of V is a lambda expander. Okay, so every single one of these neighborhoods, when I take the graph induced on them, should be a lambda expander. And then thirdly, I'm also going to require that G itself is an expander. Let's say that it's a lambda prime expander, where lambda prime should be less than 1. So I just want non-trivial expansion for the whole graph. Okay, so these are the 3 conditions that I want. So, right. Let's just give like one example of a graph that's going to satisfy this property. So a really easy example is just the complete graph on n vertices, because what happens when you, okay, complete graph on n vertices, clearly an expander, clearly connected. Now think about the neighborhood induced on any vertex, or sorry, the graph induced on any vertex's neighborhood, you get complete graph on n-1 vertices, also clearly an expander. Okay, so here we have an example of a very, very dense 2-dimensional expander. But actually, really surprisingly, maybe, okay, so surprisingly, there also exists sparse, so degree order 1, 2-dimensional expanders. Okay, and there are a couple of different groups that you can credit with the first construction of these. So I'm just gonna write down kind of the pioneering constructions, but now there are a bunch more. Okay, and I'm in a whiteboard talk, so I don't have time to write them all down. But for example, there's Lubotsky, Samuels, Vishne, /Lee, /Cartwright, Tselil, and Juke, maybe? Not sure how to pronounce this. And then there are more now. Okay, these constructions kind of come from the, I think, early 2000s. And yeah.
You say order 1, what is it, like for 3?
I don't think for 3, but I think, yeah, like a constant, and think of the size going to infinity. I mean, it's like pretty incredible that these objects, what?
So crazy, you would have thought it's not possible. But...
Yeah, I also kind of would have thought it's not possible. It's weird that this is, I agree that this is a weird thing. And okay, and the thing about all these constructions is that they're algebraic, right? So they're based on taking some kind of Cayley graph and doing some stuff to it. Okay, so for me, that means that I'm not going, I mean, okay, so for me, that's kind of a less satisfying than a situation where you have a nice distribution over expanders, because for me, it really helps me to think about the object if I can think about a distribution for sampling from it. Okay, and then also remember what I said about the case of expanders themselves, like the fact that we know that a random graph has this expansion property gives us some kind of notion of the abundance of this object. Whereas if you only have a couple of algebraic constructions, it's not clear if this is kind of like a natural thing or if it's kind of a freak of nature situation. Yeah.
Standard expansion, I care about it a lot because of mixing of Markov chains.
Yeah.
Why would I care about it? Sorry.
Okay. So that's a great question. So I'm about to tell you a theorem which is going to make you care about this question. So it's almost as if I told you to ask that. Yeah.
These constructions are explicit, right?
These are explicit constructions.
So is there some way to show that like a random plus small adjustment or something?
Yeah, like what if you take a random regular graph and delete all the local things?
Yeah, I'm going to talk about this. So in 1 second, I will address these questions. Okay, so here's so you might ask why are two-dimensional expanders interesting? So here's a theorem which I think really gets to the bottom of this, and this is called the trickling down theorem. And I guess it's due to Oppenheim, but similar ideas were previously, I mean, much long ago, also used by Garland. Okay, so what it states is that if G is a lambda two-dimensional expander, with lambda less than half, then automatically from the connection of G and this lambda expansion of all of the links, you can drop 3, you get it for free. Okay, so the second eigenvalue of the graph itself is going to be an expander with eigenvalue at most lambda over 1 minus lambda. Okay, so notice that this is a non-trivial bound. This is less than 1, exactly when lambda is less than half. And okay, here I'm cheating a little bit because really I want this to be some reweighting of G, but let's not focus on that for now. That's kind of like a subtlety. Okay, so this is really amazing. This is an amazing theorem. The proof isn't very difficult, but the amazing thing is that somehow expansion of the whole graph, which is a very global property, is being witnessed locally. Like all I have to do is I have to give you the pieces of graphs of the neighborhood of every single vertex. I don't have to tell you how they're fitting together, but already you can check if the whole graph is an expander.
Wait, I'm missing something very basic.
Yeah. No. Sorry. So okay, this isn't. Yeah, good. I shouldn't have stated it like this. So let's say that if G only satisfies conditions 1 and 2, so if it's 1 connected and 2 for all of the vertices, the link V has second eigenvalue, right, is a lambda expander with a lambda less than half, bounded away from half, then this is true. Okay, so it's like I assume 1 and 2 and I get 3 for free. Thank you for calling me out. This was really confusing what I said. Yeah. Okay, so this is the remarkable thing about this two-dimensional expansion is that global expansion is witnessed locally. And this is really useful in applications because you can witness global expansion locally. So for example, like expanders are useful in error correcting codes, but with higher dimensional expanders, we can get locally testable codes, right? There are new constructions for locally testable codes. So I mean, okay, or at least with objects that are kind of similar to high dimensional expanders. I mean, maybe, but this local to global phenomenon is really, really useful. What do you mean?
Like the proof.
Oh, okay. So I'll tell you something that's like really, I mean, it's not going to give you intuition for the lambda equal half, but think about taking a random walk on the whole graph. Okay. Somehow I can write it as a combination of random walks on each of the vertex neighborhoods, right? I can kind of decompose it in this way. And when you do this decomposition and you're clever, then you can get this result, right? So if you have extreme enough expansion in each of the local neighborhoods, this gives you expansion globally. Yeah. Question. Okay, so great. So then the starting point of this work is the following question. So are there natural distributions over sparse two-dimensional expanders. Yeah, it's like I know it when I see it kind of thing, you know, but okay, like here's something that's not like a natural distribution. Take, you know, take each one of these constructions and take the uniform distribution over them. Okay, that's kind of like, it's a little, it is a distribution, but it's not natural. Okay, so I want a distribution that will help me understand whether these what these two-dimensional expanders are, and whether they're like abundant or rare. Okay, so it's a qualitative thing, but this is what I want. And let's just verify for a second that the natural things that you might do fail. Okay, so here's an example. So let's just start off with d-regular graphs. I mean, why not? They're expanders. Why shouldn't they be two-dimensional expanders? So let's look at a random d-regular graph. Okay, so one thing about random d-regular graphs is that they're famously locally tree-like. Right, so if I look at the neighborhood of some vertex in a random d-regular graph, if we're in the situation where d is much less than root n, okay, so average degree less than, can you guys see if I write down here? Yeah, you can at least see it on the screen. Okay, so if I'm in a situation where d is much less than root n, then the neighborhood around a vertex is going to look like kind of like a tree, right? But then what is the induced graph on the neighbors of any vertex? It's just an independent set. Like I said over here, right? I cleverly set this up so that I wouldn't have to redo this example. And then the point is that in an independent set, the second eigenvalue is just 1 because I have a bunch of disconnected components. Okay, so this is a bad example. And yeah, we could go through a bunch of other natural guesses that you might have, like error-distributed graphs, same problem. All of these kind of first things that you would try seem to have a bound at degree root n. So now, like, let's relax our goal. I mean, ideally, I'd like to have a constant degree, a distribution with constant average degree over two-dimensional expanders, but even getting something with average degree less than root n would be good. Okay, and indeed, this is what we can do. So let me just say, first I'll say what we do, and then I'll tell you what the distribution is, and probably that will take all of the time that I have, but I really wanted to tell you guys about the proof, so let's cross our fingers. Time for that. Okay, so basically what we're able to show is that for arbitrarily small polynomial degree, there is a nice distribution over two-dimensional expanders. So for all epsilon greater than 0, there exists a distribution over n to the epsilon average degree two-dimensional expanders, which furthermore have lambda strictly bounded away from half, so half minus delta for delta constant. Okay, so the expansion is good enough that we trigger this trickling down theorem, and local expansion witnesses the global expansion. That's the point. So I'm just going to tell you what this distribution is, and then I'm going to at least, I'll just tell you what it is, and then I'll state the theorem more concretely. But the distribution is the distribution over random geometric graphs on the sphere. Okay, so I'm gonna define the following distribution over graphs. It's the random geometric graph distribution over the d-dimensional sphere with n vertices and edge probability p. So how do I do this? The way I sample it is I first sample n vectors uniformly at random from the d-dimensional sphere. Okay, so here's my sphere in d dimensions. Okay, I'm going to sample one vector, two vectors, etc. These are going to be like the vertices of my graph. Okay, and then in the second step, I'm going to add edge ij to my edge set if and only if the inner product with ui and uj, the corresponding vectors, exceeds some threshold tau. Okay, so what this means is basically I look around U1 and I kind of draw a spherical cap so that everything inside the spherical cap has projection at least tau or larger onto U1, and then I add an edge between these guys. Okay, and what I'm going to do is I'm going to choose this threshold tau. So I choose this so that the marginal probability of any edge is just p. Okay, that's where this parameter p came from. So this tau is something that I choose in advance before sampling anything else. Okay, now the marginal probability of any edge is p. So I get a random graph where the average degree is n times p. And yeah, and this is it. Okay, is the definition of this distribution clear? Yeah, cool. Not making these markers like they used to.
So you're not getting constant degree.
We're not getting constant degree. Yeah, I mean, remember how I like moved the goalpost here a little bit. So that was a. Not logarithmic yet. I'll tell you the theorem right now, and then yeah. So here's our kind of main theorem. So for any constant epsilon, there exists some other constant, also depending on epsilon, such that if you choose d to be c epsilon times log n, then a graph sampled from the random geometric distribution in d dimensions with n vertices and edge probability 1 over n to the 1 minus epsilon, so meaning average degree and c epsilon. Then G is a 2-dimensional expander with lambda equal to half minus delta with high probability, and delta is exponentially small in 1 over epsilon. Okay, so if epsilon is a constant, then this is bounded away from half by a constant, and if epsilon is sub-constant, then it's not. But still, you know, we have some kind of guarantee on the eigenvalues. Okay, and also G is connected, I guess. Connected.
Is there any limit known for general two-dimensional expanders?
What lambda can be in terms of G? Not off the top of my head. I mean, not these constructions, but some of the following constructions can get lambda to be arbitrarily close to 0. Okay, so.
I mean, like, you know, for general things, we know for T, you can do two.
Oh yeah. Like you mean like some kind of like alone style bound? Not to my knowledge. You.
I mean, I guess like poly D, but I don't know whether it's like square root or something else.
Yeah, like what the Ramanujan threshold would be. I guess probably couldn't get something that would.
Can you get 1 over square root D?
Probably you can, if you back solve to figure out what lambda can be in order to get the Ramanujan bound for the whole graph, and I would guess that that's some kind of bound, but I don't know if anything sharp. I don't know if it's known what's the sharp.
Yeah, so actually those constructions, the algebraic ones do have like the second eigenvalue of the overall graph, like order 1 over root D, but I don't think that's witnessed by the trickle-down theorem. Like trickle-down gives you something worse.
Yeah. Okay, so right, so this is our theorem, and my feeling is that this is a fairly natural distribution. Okay, again, I said I know it when I see it, and here I'm not objective at all, but I think this is a pretty natural distribution over graphs that are at least sparse-ish 2-dimensional expanders. Okay, so this is the main result. How much time do I have left? 5 minutes? Okay, in these 5 minutes, maybe I'll just give like a tiny taste of what the proof would look like, because this is where also the application to learning will show up. But okay, but so first of all, like, why might you expect that a random geometric graph would give you two-dimensional expansion? So I'll say something really, really hand-wavy, which isn't very precise, but maybe I can follow up later and strengthen this a little bit. So, okay, so what you want kind of is that within the neighborhood of every vertex, you're more likely to have connections than the ambient edge probability. But in a geometry, right, this is kind of exactly what we have. Like if I have some vertex I, and it's adjacent to both J and K, and somehow these edges are coming from some kind of underlying geometry, then J and K are also a little bit more likely to be close by, right? So this is one intuition why this might be a good place to turn to look for this kind of thing. Okay, so triangle inequality, I'm just gonna write here.
So you have to show that random graph with cap is going to be.
Exactly. Okay. Now let's talk about the sphere. This leads in just so it leads in so perfectly to what I was going to say. So okay, so now we're in a sphere, right? We have a random we're doing a random geometric graph on a sphere, and let's think at first of the random geometric graph as being like some kind of discrete approximation to the sphere itself. Okay, so G itself is going to be kind of like, this is some kind of a approximation to the sphere, right? G is a discrete approx to the sphere. But then what is the link of a vertex V? Well, remember that we said that we were just going to, if this is some vertex V, its corresponding vector, its neighbors are just going to be all the other vectors that fell into the spherical cap around V. Okay, so this is some spherical cap of measure P. And so the links in this graph, if we use this kind of same idea that, you know, we basically are getting some kind of discrete approximation to the geometric object itself, the link of V is going to be approximately like a spherical cap. Of measure P. Now, the cool thing about the sphere is that if I'm in high dimensions, right, like remember that I'm taking my dimension growing to infinity with n, then almost all of the mass, of the probability mass in the uniform distribution over this cap is here at the boundary. Okay. But if I just take the boundary itself, what is this? This is a sphere in one lower dimension, right? Because I'm fixing the value in this coordinate, right? And now I'm just looking at a lower dimensional sphere. And so somehow the whole game is if you can show that if you can show that the sphere is an expander, then automatically you should also get that the cap is an expander. What we do is it's not quite automatic, but it's like close enough to automatic. Okay, so our first step is to kind of prove like a meta theorem about the eigenvalues of random restrictions of graphs, right? Like the sphere is kind of like an infinite graph. This cap is also kind of an infinite graph. And when I take a random geometric graph, I'm sort of taking a random restriction, right? I'm just subsampling it. Okay. Okay, so in the proof, step one is to prove a meta theorem about random restrictions, about the spectrum. And actually this meta theorem, I think, could have applications in other situations. Like, for example, one thing that it automatically gave us is it gave us an understanding of the spectrum of the sphere itself, okay, which gives a bound on the eigenvalues of random geometric graphs, which is the first like kind of type characterization of the spectrum of random geometric graphs. And this I think should have a lot of applications in data science, right? Because, you know, we can model distributions over graphs as random geometric graphs in some cases, and there it's like very useful to understand the spectrum for applications and algorithms. So I can talk more about that maybe after if you're interested. Okay, and then step 2 is really to kind of understand the spectrum of the sphere. So in step 1, really what I mean is that it's a statement of the form like, if random walks mix really fast on the original graph, then the eigenvalues in the random restriction are good. So then we need to understand what is the spectrum in the original graph. Okay, and then this still doesn't say anything about about why we need to take the average degree to be constant, but this is maybe some calculation that I was like in my wildest dreams going to do, but I guess I'm not going to end up being able to do. So effectively, this is kind of what's going on. Maybe I can just conclude with one open question. I mean, I guess maybe it's kind of obvious, but okay. But what you might ask is, here's a question. So we know that for this distribution, our bounds are sort of tight. So you shouldn't be able to get a sparse, like a polylogarithmic average degree or constant average degree construction based on the sphere. Okay, but maybe there's some other geometry where you can do this. So is there a different geometry where a random geometric graph will yield constantly sparse two-dimensional expander? So something that we know is that you can't just take an arbitrary geometry and have this be the case. And I'll give you one, maybe I'll just give you one example to make it concrete. Okay, so remember that the whole point is that we want that local expansion witnesses global expansion. But I'm going to show you 2 different geometries. One of them is a globally expanding geometry, and the other one's only locally expanding geometry. Or sorry, one of them is a globally expanding geometry, and the other one is a not globally expanding geometry, and the local neighborhoods are going to look the same. So the example I want you to have in mind is in the first case, we have the expanding, just a graphical metric with a regular expander. So here I've got like a deregular expander. So a deregular expander, it can also be a metric space where every vertex is a point in the metric space and distances are defined by the graph distance. And you could have a random geometric graph in this space with some kind of whatever distance threshold you want. And on the other hand, I can have 2 deregular expanders on n/2 vertices, which are connected by a bridge. So this is a deregular expander, and this is a deregular expander. But there's a really sparse cut here. But the point is that the local neighborhoods look the same. Okay, so this is just to say that like a generic geometry isn't going to work out for you. You need a special property of the geometry. And the kind of cool thing about the sphere is that just by seeing a single link here, you can tell what dimension of sphere you're in. You kind of like the curvature tells you what kind of sphere you need to be in. And so this tells you that you have an, I mean, this says that this is an okay geometry to look at. But I don't know which geometry will be better than the sphere. And if you have any thoughts, I'm really excited to hear that. That's all I had. So thanks.
To wrap up this session, you want to say something?
Oh, well, maybe like since lunch is now, like maybe if you want to, for people who are interested, you want to like casually, let's break, but I mean, maybe if you want to casually show the calculation you want to show on the whiteboard,
Oh, sure, yeah.
like I'll stick around.
Cool.
And then we can reconvene it.
At 2 o'clock is the next session.
2 o'clock is the next session.
Thanks.